So in this lecture we will see the operation of DC-DC isolated converters. We will start with the buck derived converters. We'll start with buck derived DC-DC converters. So buck derived means, as I told you in the last lecture, that say this is V in plus minus, and so basically if you draw the output section of a buck converter, so you will find that there is a freewheeling diode sitting at the output side, then we have a LC filter, and then a load. This is V0. So basically what we are trying to do is, and there is an isolation. Our aim is to give the isolation. So the negative terminal of V in should not be connected to negative terminal of V out. So switch, we have a switch S1. Apart from the switch, we have a transformer N1, N2. So our aim is to integrate this switch and this transformer in the input side of the buck converter, so that we'll get a buck derived DC-DC isolated converter. So if we draw, this is, let's say this is A and B. If we draw the voltage of the waveform AB for a conventional buck converter, then what we have is of a conventional DC-DC buck converter. So when this, so assume that there is no transformer and the switch is directly connected between say this is C and D. For a non-isolated DC-DC buck converter, terminals B and D are directly shorted, and between C and A there is a switch S1. So which is a conventional buck converter. When switch S1 is on, the voltage across D1 is plus V in, and when it is off, the diode is forward bias, it is voltage across the diode is 0. So this is V in 0, V in 0. This is the trend, or this you can call, so this is the waveform of the voltage VAB. Okay, so basically what we have to do is, if you are saying that we want to derive a buck converter, DC-DC buck converter using a transformer, so say this is VS and this is VP. So our aim is to have VS approximately equals to VAB, the waveform wise. So our aim is to integrate the switch S1 and transformer in such a way that what we will do is, the secondary induced voltage of a transformer, the trend of the waveform will keep equal to that of VAB. So what we'll do is, we'll connect a switch in series with the primary of the transformer, and the secondary, what we will do is, we'll directly connect it VS to VAB. So this will yield like this. This is V in. I'm not drawing the voltage source. This is NP, and here I will write NS. This is the dot convention. This is VP. This is the secondary NS. This is VS equals to VAB. So after that we'll have the conventional buck converter circuit. So this is the topology of a isolated DC-DC buck converter. Okay, but however, there is a very big issue with this type of circuit connection. The issue is that as we discussed in the last lecture, we saw about the volt second balance for the transformer, that if using this BH curve, what we saw is that For the transformer to be a integral part of a DC-DC converter, the core has to be powered. So basically it has to be magnetized and demagnetized in either of the time instances. Say that when switch is on, say that the transformer is magnetized, so its primary is connected to the supply voltage. So so basically if you see the inductance Lm, so you can say that the inductance Lm is getting charged from input supply. So if Vn is constant, the Im will be Im is what VL is L di by dt. So IL is 1 by L integral VL dt. So integration of constant V in term is a ramp signal. So Im will be rising. But here what happens is that when the switch is on, the V in, so when S1 is on, so if we have this inductance, this will say that it is like this, and this is I1 dash, this is Lm, and this is Im S1, and this is V in. So this I1 dash component, I1 dash, you can write as I, so say that this is I2, so it is I2 dash, which is nothing but I2 into, so Vp by Vs is Np by S, Vp by Vs is Np by Ns equals to Is by Ip. So basically if you are transferring the secondary current to the primary side, it should be multiplied by Np by Ns. So Np by Ns. So basically what I'm trying to say is that this current I2, this is Id, and this is IL, this is IC, and this is I load. So what I'm trying to say is that this component of current I2 has a part which flows through the inductor, or which is a load component. So it is load dependent current. It's only that when the switch is on and off, what happens is based on the induced voltage Vs, the nature of I2 will be governed. So if S2, so if S1 is on, the V in voltage will come across Vp. So the voltage across secondary Vs will become what? Ns by Np into Vp. So we can write Vs as Vp into Ns by Np, or you can write Vp dash. So in when S1 is on, Vp is V in, so Vs becomes V in into Ns by Np. This is the voltage induced across the secondary. So a positive voltage is induced across the second terminal Ns, which means that the diode D1 will be reverse bias. So ID will be 0. So whatever is the I2 current, that is nothing but the inductor current. Okay, and inductor current, we are assuming that inductor current, the inductance is such that it is continuous mode of operation. Means it has some average value governed by the load current, and the ripple flows to the capacitor. And when the switch S1 is off, typically what should happen is that the inductor current IL should free wheel through the diode ID1, which means that if the diode D1 is conducting, the voltage across secondary will be 0, because now the inductor current wants to free wheel. So say that S1 is turned off. Initially the voltage across Vp was V in. Now S1 is turned off. Now the analysis of the circuit starts from the secondary side. The inductor current try to free wheel, so it forces the diode D1 to turn on. If the diode is turned on, what happens is the voltage across it becomes 0. So Vs becomes 0. In that case, what happens is I2 current will be 0, because the secondary will not come into picture. So if Vs is 0, then Vp will also become 0. So what happens is, this is Vp. If you plot Vp, I hope you got some idea of operation of this circuit. When S1 is on, Vp is V in. When S1 is off, V in is 0. Okay, this is the time. So this waveform of VAB is equals to waveform of Vp, and waveform of Vs will also be like Vp. If you draw the waveform of Vs, Vp comma Vs, so I will draw using some other current, sorry, some other color. It will be like this. Vp comma Vs. So this will be V in into what? Ns by Np. And in this case it will be 0. Okay, so I have plotted Vp and Vs versus time. This will be the nature. What happens is when the switch S1 is off, which means that the primary will become short circuited. So if the primary short circuited, the current Im will freewheel in this path. So basically what happens is, if the current Im tries to freewheel, because it's short circuited, so basically Vp, the voltage across the inductance Lm, the big inductance Lm, will become 0. So naturally the current will choose the least impedance path to freewheel. So what happens is, during the case where S2 is turned off, the transformer operates in the region number 3. Initially starting when say that B is 0, H is 0. When the switch S1 is on, the core will be magnetized slowly. So it starts from 0 and it will follow this trajectory up to some time. Okay, it may not hit the saturation, but it will rise like this. The inductor current Im will rise. And when the switch is off, from this point what happens is, this will shift from here and again it starts to fall. But the thing is, the time for falling is limited. What is this time? 1 minus d into t switching. So what happens is that this Im has to be 0. So this trajectory should reach here, should touch at least this point. At this point Im is 0. Even at this point Im is 0. So while it is while the core is getting demagnetized, we have to give sufficient time for it to be demagnetized. Why? Because if say that it hits till this point where Im is not 0, Im is some negative value, means the current is getting built up in so the current is falling from the initial value. The current is falling and going to negative. So basically forget about negative value. Current is of one direction only, so it will not even go into the second quadrant. It will be in the first quadrant only. Okay, it will be in the first quadrant only, where Im just falls. Im will not be negative. So it follows this straight line instead of this. It follows this straight line. Forward converter follows this straight line. So the BH curve, okay, I'll redraw the BH curve. There is no big thing in it. So we'll draw B, and here we'll draw H. You can write it as phi m, and here you can write it as 1 by Lm integral Vp dt, because this is proportional to phi m, this is proportional to this. One is proportional to mmf, other is proportional to the magnetic field, magnetic flux. So it will start from this point and it will rise when S1 is on. This is when S1 is equals to 1. Then what happens is, when S1 becomes off, so it will come here. This is Im. You can write as or Im. So the slope, if this is Im, okay, I will remove phi m and I'll write only Im. So this slope is LM. What happens is the current, magnetizing current should touch 0 before in this time 1 must be into T switching it should at least touch 0. What happens is if it does not touch 0, if it lies over this point, say this point, in this case there is some finite IM. What happens is now this is IM of 0 for the next switching period. This will be IM of 0 for the next switching cycle. Okay, so the voltage seen across, so yeah, this is the IM of 0 for the next switching cycle, and IM of 0 at the end of each switching cycle should be the same. So given that the D is not changing or T switching is not changing, it will be this same only. But the biggest concern is the voltage seen across primary will be 0, but there is no actual physical path for this current to discharge. There is no path for IM to discharge or demagnetize the core. So this we have to make sure that IM of 0 for each switching cycle at the end of each switching cycle should be the same, so that the core will not be magnetizing or the flux walking phenomena will not happen. So a circuit provision is needed for discharging IM in T equals to T off. There should be a circuit provision. So in the present circuit there is no provision, there is no path. So just like so what we'll do is we'll copy the fundamentals which you already used while designing the DC-DC converters. So we added this diode D1 for the current IL to freewheel. Similarly, what we'll do is we'll add a diode across it. V in S1 D2. Say this is D2. Okay. This is I1 dash, this is LM, this is IM. So when this is off, the current IM will freewheel through this diode, which will demagnetize the core. So it starts to follow this trajectory. The current falls and thus the core demagnetizes before the start of the next switching cycle. Okay, so this current IM will force the diode D2 to turn on. So the current IM will freewheel. So if we plot only the current IM, it will be like this. When the switch is on, the current IM will rise. When the switch is on, what we are saying is that the current IM falls. It falls down. And then say till here is this is T on and this is T on. This is T on and this is T off. Say that IM does not become 0. So it will again rise with the same slope and fall. So there will be some average value of capital IM. This capital IM. So what we are doing is that we are resetting the core and it operates only in the region 1. It does not go to the region 3. So that's why this converter, which we'll be seeing, is called as a forward converter. This is called as a forward converter. So what we are doing is we are resetting the core IM. Now IM may not be 0 or maybe non-zero. It won't be negative because it won't go to the region 2 of operation. So it may be 0 or may not be 0. It will be some finite value. So what we are doing is, to avoid flux walking, phenomenon, we make sure IM of n into T switching equals okay, I'll just cut paste this. This is equals to IM of n plus 1 into T switching equals to 0. Means at the end of every switching cycle, we are making sure that this IM becomes 0. Now so what happens is this diode, so D2 should be a fast operating diode or Schottky diode, Schottky power diode. So this diode should make sure that the current reaches 0. So if the current becomes 0 exactly at the instant where T equals to T switching, which means that it is a continuous mode of operation for this converter. Means IM will have average value. IM will definitely have some average value, even if the current doesn't resets to 0 at the end of each switching cycle, or it sets to 0 exactly at the end of every switching cycle, or it is becomes 0 before even the end of every switching cycle. In all the three cases, there will be some average value of IM. So what we do is, so this will be costly. So to have so with a normal diode, we add a Zener diode to make IM equals to 0 fast. So what happens is, we add a Zener diode. So what happens is, if now this IM forces diode D2 to be turned on, and thus the voltage across it becomes 0. Now what if the voltage seen by this inductor LM is negative? If the voltage is negative, in that case the rate of fall of IM will be more than what? Then compared to when there is no any additional element. So what my idea is to have a circuit element that will make the voltage across LM for S1 equals to off to become negative, so that IM falls quickly. If IM falls, so this is IM1, so IM will fall quickly. These are the different time instances, so IM will fall quick. Okay, so this and this, so these slopes, these are the slopes. What decide the slopes? By Vm when S1 is off. So if you have a negative voltage across Vm, then LM, then what happens is the device will be, the rate of fall of IM will be more. So what we will do is, we'll add a Zener diode. So Zener diode will try, the basic working principle of a Zener diode is that a Zener diode acts as a normal diode when the current through it is less than the limit of the current. and will try to maintain the voltage. When the current through which is flowing through the Zener diode is increasing, what will happen is that the Zener diode will consume that extra amount of current, whatever is the excess current, and will always try to regulate the voltage across it to the rated voltage. This is a Zener diode. Say this is V, is V1, and this is V2, and this is some I2, this is VZ, and this is what, IZ, and this is I1. So V2 is equals to VZ, which is almost fixed. VZ is fixed, and VZ is plus minus. If this convention, then this becomes minus. So what happens is I1 becomes IZ plus I2. I think I did a mistake. IZ plus I2. So what happens is if I2 increases, so this I1 will also increase. So this I1 will decrease to maintain I1 almost constant, or vice versa. What a Zener diode will do is it will act as a normal diode in reverse bias. Zener diode, it will act as a normal reversed bias diode when IZ is less than IZ rated, means some small amount of current flows through it. Now what happens is when the current flowing through the Zener increases than the IZ rated, what happens in this case, VZ is constant and the excess current flowing or the excess current flows through the Zener. So the Zener action comes into picture when the current demand in the circuit is more. So basically what it tries to do is VZ versus IZ. So if we have VZ and this is IZ, it will act as a normal diode in the forward bias. This is the forward bias. It will act as a normal diode. The change in this acts when it is reverse bias. Now what happens is, for a normal diode it is falling like this. This is for a normal diode. Same, this is for a normal diode. For a Zener diode, okay, instead of this I'll use the other color. But this is same. A Zener diode has more flexibility. So what happens is this will be almost linear and it will be like this. So means whatever is the change in IL, a Zener diode will try to maintain almost constant VZ. That is VZ rated across it. Say the Zener is rated for 3.3 volts and some amperage of current VZ, and this point is called as the breakdown voltage. So all these condition 1 and 2 are in, so this is of region 1, region 2. So this is reversed bias is in the zone 2, forward bias is in the zone 1. This is a Zener diode and this is a normal diode. A Zener diode will consume whatever is the current in it in the negative direction. So means the negative direction current is this. So it will consume that current to maintain the source currents and the load current constant, almost constant, and it will also maintain the voltage across it as constant for a high range of variation of the circuit. This is the Zener breakdown. So we operate our Zener in this region, in the region number 2. So Zener diode always maintains a constant voltage across it, and its action comes into picture when it is reverse bias. This we should know. So our aim is to make our aim was to change the slope of Im when the falling state, so that it becomes 0, either exactly at the instant at the start of new cycle or even before that. So we'll show the Vp. This is Vp. We'll show the Vp some negative voltage only when S1 is off. What we'll do is we'll add a Zener. We'll add the Zener in this way. So I'll draw the forward converter. Forward converter, which is a DC-DC buck derived converter. This is Vin plus minus. This is S1. S1 is a switch or a MOSFET. So after S1 we have now somewhere around here we have to place the Zener. This is a normal diode D. What was that? D2. Okay. Then here was LM, and this is the IM, and this was the I1, and NP, NS. Then here what we have, buck derived. So basically D1 and a load. So what we'll do is, so voltage across Zener is almost constant in the negative direction. So forward is this. So this is the Zener. This is plus minus Vz, and this is plus positive direction of Iz. So the Zener action comes in the reverse bias region, which means that the voltage across Zener becomes negative polarity. This is anode, this is cathode. So when Vz becomes negative, it means that the voltage across it is reverse. So K becomes positive and A becomes negative. So as per our dot polarity, this is the dot and this is the dot. We want to show a negative voltage. So positive Vp is, so say this is Vp. This is the positive sense of Vp, this is the negative sense of Vp. So basically this should get the reverse voltage. This should be negative and this should be positive. Anyways, we are not concerned about the diode D2 because it will be forced turned on by the current Im, this current Im, when the switch S1 is off. So how to draw the diode then? So positive should be at the cathode. So, and cathode is the tip of the it. So it should be like this. This is voltage VZ. Then what should be the current through it? The positive direction of current is from anode to cathode. So we'll follow this particular notation only in the reverse bias region, or we can change the sense in which we are doing. So now this is called as a forward converter, NP by NS. So this is VS. VS is VP into what? VP by VS by VP is NS by NP. So it is NS by NP equals to VP dash. Rest will be same. The operation will be same. So what happens is when the switch is on, so first we have to see by addition of this zener, is there any effect on the circuit when the switch is on? It ideally should have no effect. So when the switch is on, the voltage V in, so we'll say this is VS1 plus minus IS1 is equals to I1. So for every element, because now we are seeing the steady state operation of a forward converter by plotting all the waveforms of all the circuits, so of all the circuit components. So V in is there, S1 is there, so voltage across S1 and I1, then VZ, IZ, then VD2 into so VD2, ID2, that we will plot anyways. So but we are just seeing the operation of this converter. When the switch is on, plus polarity comes across the what? This is anode, this is cathode. Anode of the this diode, the Zener diode. So this will forward bias the Zener diode, and you know that in a forward bias the Zener diode acts as a normal diode only. So there is no difference in the operation. But here what happens is the negative terminal of V in is connected to the D2 always. Let the switch be on or off, it always. So D2 turns on forcefully only if IM has to freewheel. Okay, there is no other chance for D2 to turn on because D2's anode is always connected to the negative. So D2 will be reverse bias. So if say this is D3, if D2 is forward bias, if D3 is forward bias and D2 is reverse bias, so this path will have no significance, it will be open, which means that the VP equals to V, and so the voltage across the primary. So instead of drawing here VP, I think I should draw here. What is this? This is VP and this is VS. So VP is V in directly and VS is V in into NS by NP. So then this will becomes dot polarity, this becomes plus, this is minus, so minus is connected to the anode of D1, so it is reverse bias. So this is IS, this is ID1, this is VL1, this is IL, not the L directly, right? VL, this is IL, this is C, this is IC, and this is V naught. So ID1, yeah. So it acts as a normal buck converter, isolated buck converter for forward bias. For reverse bias, what happens is when S1 is turned off, now the analysis of the circuit starts from the primary to the secondary. We should not go from secondary to the primary, so for analyzing this we saw from secondary to the primary, because our aim was to make this converter operate just like a buck converter. So the secondary part of the after the transformer is similar to the buck converter. So that's why we thought that D1 is short circuited, so secondary short circuited, so VP should be short circuited, which means that the core is demagnetized. But now that we have a converter, we'll start to analyze it from the source to the load side. So when S1 is turned off, which means that the voltage source which was supplying or energizing the core has removed. So IM will forcefully turn on D2. So D2 is forward bias now, irrespective of the fact that its anode is always connected to the negative, but it is turned on. That is the forced commutation. So in that case, what happens is, and the switch is on. So if you apply simple KVL, V in equals to VS plus V in is VS minus of VZ. in this loop. So the fear was, if there was no switch sitting here, then V in and VZ will be directly connected to each other, which will damage the Zener diode, because V in is some other different value and VZ is some other different value. If we just connect two voltage sources across, so we can consider Zener diode as a constant voltage source in the reverse bias region up to the breakdown voltage. So it will result in the very high current to flow between the Zener and the this thing, which may which may also avoid the or reduce the demagnetization of the core. So as this switch is sitting here, which is open, so V in is not directly connected to VZ because D2 is forward bias. So V in is VS1 minus VZ. So VS1 is V in plus VZ. So our Zener diode is protected. So IM flows to D2, D2 is forward bias, and the voltage seen VP becomes, initially it was 0 because there was no Zener. Now it is V in VP becomes what? If this is the dot polarity, this is plus. So across it negative is connected. So VP is minus VZ. So negative polarity of voltage is connected across the primary, which means that the rate of fall of IM is faster, like this. This slope of falling of IM which you see here is faster. So thus IM demagnetizes, and as IM demagnetizes, this negative voltage comes here. So if then VP becomes minus VZ, then VS becomes minus VZ into NS by NP, which means that here some negative voltage is induced because it is a transformer. So as we know, the transformer operates on AC voltage of both the polarities, so it will induce the voltage in both the cases. In that case, the anode of the diode D1 is connected to the positive terminal. So D1 will be forward bias, which means that this current IS will become 0 and ID1 will be equals to IL. So it will behave as a normal buck converter only, even if S1 is off. So this becomes our buck derived isolated DC-DC converter, which is called as a forward converter. In this case, the forward converter, the transformer operates in this is not the thing. Yeah, BH curve. It operates only in region number 1, which operates only in the forward region. That's why the name is derived as forward converter. So IM just becomes 0 to some IM, which is equals to the value which is equals to this peak value. So if we just draw the waveform, say that we want to draw all the waveforms of this converter. So yeah, we'll start with the gate pulses. Say that this is the gate pulse for S1. This is for S1. 1 0 1 0. So we just have to extend it down and plot all the steady state waveforms of the converter. So S1 is plotted, the switching pulses are plotted. We start with the circuit components from the primary side. Vin is done, then we'll draw VS1 and IS1 or IL. This IM is there, and I forgot to draw one more section here. So this is I1 dash. So here I1 will be equals to minus of IZ plus I1 dash. So this minus of IZ will come picture only when it is off, and so it will be there when it is off, and this will be there only if it is on, which means that when the switch S1 is on, the I1 equals to what? I2 dash, and I2 dash. Okay, and when the switch is off, I1 will be equals to IZ, and in that case Iz is equals to Im because due to is forward bias. So I can write simplify as in two ways. I1 equals to what? I2 dash. I'll just write the relation again. Vp by Vs is Np by Ns is equals to I S by Ip. So the primary current referred to the secondary current referred to the primary will be Is dash will be Is into Np by Ns. This is what is the I1 dash current. Means basically you have to transform the secondary current to the primary. Or I think the reverse relation holds. So we have to draw I1 dash. I1 dash is the seen at the primary. So it is Is into Ns by Np. So here it is I1 dash and here it is Is. And when the switch is on, the diode D1 is off, Is equals to what? IL. So it is IL but multiplied by Ns by Np when S1 is on. Similarly, what is I1? When S1 is off, when the switch is off, it is equals to Iz and other equals to Im. So for this equals to Im, we'll first draw the Im current. This should be the start point of this. So basically our aim to add a zener was to have a margin. So this is called as the margin. This is called as the margin. So means it is Im is discontinuous in nature. We'll draw Im quickly. So basically initially when the switch is on, Im rises and it falls. So this is the discontinuous in nature. Again it rises and it falls with the same falling time. This waveform belongs to Im. This is Im waveform. Similarly, we can plot the waveform for phi m, Im or phi m, because Li is n phi. So there is a linear relation between I and phi that we can easily plot. So phi becomes L by n into I. So here phi is less and I is more. So this is Im and this is phi m. So this is due to Vz. This is for safety, or you can call it as margin. So this is Im, or it can be up to here, not an issue. Only the waveform will change. So we have drawn Im. So Vm equals to Vp only. So we'll draw that later. Vm equals to Vp only. So now we'll draw the switch current and voltage in a single plot. So first we will plot the Vs1. When the switch is on, voltage across it is 0. So it is 0. Whenever it is on, when the switch is on, it is 0. And when the switch is off, the voltage across it is what? Vin equals to minus to plus, then plus minus and minus plus. So V in will be added to Vz and that will be equals to equals to Vs1. So Vs1 is V in minus Vz in the plus polarity. V in minus Vz when the switch is off. This is 0 and this is V in minus Vz. This is Vs1. Now we'll draw the Is1. With Is1 or I1. I1 is IL into NS by NP. We know that even if the current Im is discontinuous, but the inductance L, this L, is such that the current is continuous. So we just want to draw the continuous current. So basically like this I'll draw. Oh. So this slope is IL into what? NS by NP. NS by NP. When it is on, this is comma IS1 or I1. And when it is off, it is equals to Im. So this equals to Im. So it becomes like this. Vs1 becomes this nature. This is equals to Im. So switch is done. Next comes what? Next element comes so there is no meaning in drawing the waveform of the Zener diode, because when the switch is on, the Zener diode is forward biased, so Vz becomes 0. When it is off, Vz becomes Vz, constant Vz. So Vz, I can just, if I just draw on the right side, it will be so it will be what? Yeah, 0. And then what? When it is off, V minus Vz. So there is no meaning in drawing the Vz because Vz is constant voltage. There is no meaning in drawing the constant voltage because we have to draw Vs1 as a function of Vz. We can't draw Vz is a function of some other independent term. Vz is itself an independent term. So the voltage across the switch is V in minus Vz when it is off and it is 0 when it is on. Zener is done. Now the diode D2. VD2 and ID2. VD2. First we'll draw VD2. The diode is off. So it is off during the on time of the switch. And oh sorry, then the voltage cannot be. Yeah. So when the switch is on, the diode D2 is reverse bias and the voltage across it is becomes what? The switch is on. V in becomes Vz. So this is plus, sorry, this is plus and this is minus. Minus plus, minus plus, minus plus. So V in plus Vz plus VD2 becomes 0. So VD2 becomes minus of V in plus Vz. Minus of V in plus Vz. Oh, I made a mistake. It will be V in plus Vz in this case. V in plus Vz. And here it is 0 during off time. So what we saw that the voltage V in plus Vz appears across the switch in positive polarity when the switch is off, and the same voltage V in minus Vz appears across the diode D2 VD2 as a negative term because the diode is for reverse bias during the on time, and during the off time of the switch, the diode is forward bias. So voltage across it is 0. So it goes below the 0 line. VA2 is V, anode to cathode. This we are drawing. So when the diode is reverse bias, the current through it is 0. Comma I D2. The diode is reverse bias, the current through it is 0. I is magnetizing, but there is no role of diode D2 and the diode and Zener branch in the forward bias thing. So the current becomes 0. And ID2 equals to, this is the ID2. In this fashion. I capital D2. The current becomes 0. And when the diode turns on, when the switch is off, the diode D2 is forward bias. ID2 equals to what? IM. What was IM? Yeah, this was IM. So from here to here, again from here to here, it will be like this. This is ID2, current ID2, and the current and voltage through the diode D2. The input section is done, the diode and the Zener branch is done. So I think I can draw one more current here, comma IZ. So again, during on, the current IZ equals to ID2, both is 0. And when the this is on, then IZ becomes equals to ID2. So IZ equals to ID2. So I can use the same current, ID2 equals to IZ. Like this I will write. ID2 equals to IZ. And VZ is a constant term. Then we'll draw VP and VS. When the switch is on, VP becomes equals to V in. This is VP. And when the switch is off, VP become equals to what? Minus VZ, because that D2 is forward bias and S1 is off. VP. This is V in, and this is minus of VZ. This is VP. I1 dash current. I think I1 dash current. Now I1 dash current. I1 dash equals to, I1 dash is nothing but IS into what? NS. Okay. Current I1 dash is nothing but IS into NS by NP. So during, so now if you want to write IS, what will IS be? when S1 is on, IS becomes equals to IL when S1 is 1, and IS is 0 when S1 equals to 0. So same thing we can substitute here, I1 dash. So I1 dash and IL, just we can write, okay, I'll plot I1 dash also here. So this was IL, right? IL into NS by NP. Yeah, IL into NS by NP. So I think I should use the same red color which I used here. I1 dash, because I1 was equals to I1 dash when S1 was on, and I1 dash is equals to IL into NS by NP. So the same waveform should come here. Which is IL into NS by NP. Okay, that was I1 dash. When it is not there, what happens? The current becomes 0. IS becomes 0. So therefore I1 dash becomes 0. This is I1 dash. Then if we draw IS, what is IS? So say that NP is greater than NS. Primary turns are greater than secondary turns. So generally, logically, VP is greater than VS. And so thus IS is greater than IP. Secondary current is greater than the primary current. So it will be like this. This is equals to IL. I hope you understood the waveforms VP, I1 dash and IS. I1 dash equals to IP. So I1 dash is nothing but IP. So now I think primary side is done. Now comes the secondary side. Secondary side VS is VP into, I think VS1. Okay, that is VS1. IS is already done. VP is there. Now what is remaining? We can write comma VS. Oh, it's not visible. Okay, comma VS. So VP is greater or VS is greater? VP is greater and VS is small. So this will write. This is the voltage VS, and this is this voltage. Because it has to be less than both the cases. So the negative portion is minus Vz into NP is greater than NS. So NS by NP is less than 1 into NS by NP, and this value becomes V in into NS by NP. NS by NP. So VP is equals to VS only, but with different turns ratio and different gains. So secondary side also done. Then comes the diode. the inductor current and the capacitor. So we'll start with the inductor current basically. So our assumption was that it works in a continuous conduction mode. So I will draw IL. The inductor is sufficient that it is in continuous conduction mode. So this is IL, that is nothing but this inductor current, and comma VL, VL. When the switch is on, Vs becomes equals to Vin into Ns by Np. So it is Vin into Ns by Np minus V0. And this has some, okay. This value is V in Ns by Np minus V0. And the value of Vs when the switch is off becomes equals to minus Vz. So this becomes minus Vz. This will turn on the diode. This negative polarity voltage will turn on the diode, so it will be short circuit. So it will be minus V0 only. This value is minus V0. IL and VL. So this is A1, this is A2. The volt second balance and amp second balance should be verified for this particular converter. Then VD1, ID1. VD1 is VAK. So VD and VD1 so is equals to Vs. The switch is on. And what is Vs? Vs is V into Ns by Np. And then it becomes 0. This is V in Ns by Np, and this is 0. VD1. Then ID1 equals to IL when the switch is off, else it is 0. VD1 into ID1. Diode is done, the inductor is done, Vs is done, Is is done. So, and then comes the capacitor and second balance. So IL is equals to IC plus this. So the ripple content will be in the capacitor and the other part goes to the load. So this is IC. IC is this. This is IC. IC C into dv by dt. So v is integral of I dt. So if we integrate the positive slope, integration of x is x square by 2. So it will be polynomial. And if it is a negative x, if we integrate negative of x, it will be minus x square by 2, a falling polynomial. So basically v naught will be like this, then like this, then like this, then like this. This is v naught with some average value, and we assume that this is delta v naught. Similarly, we have delta IL here, delta IL, and this has some average value. This equals to capital IL alone and all. So we have to, I think we have drawn the waveform from this for the switch S1, which is VS1, IS1, which is and I1. And we have drawn the waveforms for the middle leg of the Zener and the diode D2, VD2, ID2, IZ. Then from the primary winding, we draw VP, I1 dash. Then for secondary VSIS. Then from secondary circuit, we draw the we have drawn the waveforms for the inductor VLIL, then VD1, ID1, then for the capacitor and the output. So if we do the volt second balance quickly, using the volt second balance, for the inductor. So what is the volt second balance for inductor? It says that similarly for amp second balance, this is A3 and A4. We saw that the waveforms of the secondary side are very similar to the buck converter. So the same principle we can apply. So we can use the same formula for finding the relation between output and input voltage. So that is A1 equals to A2. So therefore we can write what is A1, that is V in into NS by NP minus V naught into what? The time is T on, that is D into T switching. What is the other part of this? Minus V naught. So minus V naught goes to that side, becomes plus V naught. V naught into 1 minus D into T switching. So T switching get cancelled. So V in into D into NS by NP minus V naught D equals to V naught into 1 minus D, which means that V naught is V in into D into NS by NP. So V naught equals to D into V in was the buck converter. Now here additional turns ratio comes into picture. So therefore NS by NP can be set in such a way that we can change the gain, a separate gain is added, and by equating A3 equals to A4 we can get the value of the capacitance, or by using A3 equals by using A3 equals to A4 we can get that the average value of the inductor current goes to the load and the average value of capacitor current will be 0. And the same formula we can use for finding the working inductance, the required inductance and required capacitance in terms of the delta IL, delta V naught. We can find the critical inductance for the secondary side of the inductor, that is L, using the minimum load. So here by using by making the this current 0, IL minimum as 0, we can get the L critical, then we can get the C critical, then, and there is no concept of minimum load on the buck converter because anyways D is restricted to 0.1. So as D lies between 0 to 1, so D into NS into NP, which is the turns ratio gain. So in this case, this is the input to output relation. So as we said that the IM this is IM. So the IM, this is the capital T switching, and this is T on. So what happens is, this is some, say some T dash, and this is 1 minus, this is T off. So using the zener we said that it should fall, it should become 0, IM should become 0 before start of every switching cycle, at least it should be 0. So the relation, the condition for that is Vz into T off should be greater than V1 into T on and mod of it, then only IM is 0 before T equals to T off. This is the condition, selection of the voltage clamping diode. So from this we can select the value of Vz. So Vz is greater than mod of V1 into T on by T off, that is T on by T off, that is D by 1 minus T. This should be the value of the Vz. So here in this case what happens is that when the switch is off, the IM current freewheels to the diode and the Vz of negative polarity of the zener voltage is applied to the primary of the transformer, so that it is forced due to the forced turn off of demagnetization of the core, it becomes 0 before start of the next switching cycle. So it means that the energy is the demagnetization energy, the energy is transferred out of the transformer through a dissipative element. It is free will. Now there can be a provision where we can give this energy back to the source. For that a tertiary winding is added. So in that case what happens is the IM becomes negative, and thus the forward converter may operate in the quadrant number 3, in region number 2, in region 2 of operation, by using a regenerative forward converter. By using a diode and a tertiary winding, we can make sure that the energy which the transformer gives back for resetting its core or for demagnetizing its core can be sent back to the source without wasting. So here, as IM is becoming 0, the energy is dissipated. So there can be provision for regenerative forward converter of operation. And then similarly there can be, just like this relation is there, Vz T off is greater than V1 T on, similar relation can be achieved. So a tertiary, we can add a tertiary winding for regeneration, and the circuit is modified as this becomes V in, this is S1, this is NP. So here I am not drawing IM, but assume that this is IM, this is I1, IS1, and then we should have a diode. This is NT, tertiary winding. Then we have a secondary winding, NP. A diode is added here so that a negative current does not flow through the secondary winding, inducing a positive voltage across the secondary during the turn off of the switch. That's why diode is added here. So this is the forward converter with the tertiary winding. The aim of the tertiary winding is just to pump the energy which the transformer dissipates during demagnetization back to the source. So this is the tertiary winding. This is the dot polarity of the primary and secondary winding. So say this is some diode D1, this is D2, this is D3. So now there is no need of the zener and this diode D2 to freewheel and make IM 0. We have to pump this energy back to the source. So there is no need of the zener and that branch. Instead of that, we have a tertiary winding. So what happens is when the switch is off, so the transformer should dissipate and should send back this energy IM to the source. In that case, what happens is the dot polarity of the tertiary winding should be this. Why? Because the diode is sitting here. We have to when S1 is on, this circuit behaves very similar to the conventional forward converter, which is this one. We have to see then what happens in the turn off time. During the turn off time, when the switch S1 is off, the current IM should, what happens is it should magnet. So basically the NP is there. So whatever was the voltage induced across NP, the voltage induced across the tertiary NT will be NP into NT by VP into NT by NP. This particular voltage will be induced across the tertiary winding, and this tertiary winding, the current will flow back to the source. The aim is to make IM flow in this fashion. So what happens is IM will forced turn on the diode D3. In that way, the IM will flow to the diode D3 and it will go back to the source like this. This is IM. It should go back to the source. And if the dot polarity of the tertiary winding, so without using a tertiary winding, this cannot be achieved. The tertiary winding will forward bias the diode, which is also forward biased by IM. So the current IM, the current which is used for demagnetization of the core, will go back to the source. So this is the tertiary winding, and the winding relation should be, that is NT, number of turns of tertiary, by N1 into V in into T off should be greater than V1 into T on for this to happen, and mod of this. So we are done with the analysis of the first DC-DC isolated buck derived converter, which is a forward converter. In the next lecture, we will see other converters like push-pull, flyback, then half bridge, full bridge, and dual active bridge.